Hello everyone, I'm Max. Today I want to talk about something called supercritical airfoil. It is one of the few ways for airliners and business jets to reduce their drag, which can increase fuel economy and speed or both. In order to understand how this technology works, it's first very important to understand what drag is on a fundamental level. Here's the drag equation. FD equals 1/2 fluid density times relative speed squared times the coefficient of drag times the cross-sectional area. Fluid density is something that is slightly easier to deal with. As you increase in altitude, the density of air decreases, and that is the reason why many faster aircraft such as the Concorde and the SR-71 all fly at higher altitudes. The Concorde fly at 60,000 feet, which at that altitude have less than half of the air density of 40,000 feet, which is pretty much as high as you go with modern airliners. Relative speed is something that is very hard to optimize and deal with because not only is it something that you can't necessarily fix. If you want to go fast, it's a burden that you have to take. It also increases in an exponential manner. That's why it is to the power of 2. There's not much to do with relative speed in the context of drag, and many aircraft have to just bear this burden. The last term in this equation is the cross-sectional area. This can be optimized by reducing the diameter of the fuselage, which is the main contributor to this term in the equation in most aircrafts. And lastly, there is a concept called the coefficient of drag, which can be optimized by having a more streamlined fuselage and also, as I mentioned, the supercritical airfoil. Another concept to understand in order to understand how the supercritical airfoil works is the concept of wave drag. On the left of the slide, there is a graph that shows the relationship between the drag coefficient and also the flight Mach number. You can see in the middle of the transonic speed regime, there is a peak in the drag coefficient. The reason behind this is the airflow becomes supersonic, usually above your wing. The reason behind this is that your wing is a solid object, and as it travels through the air have to make way. And in order to do that, the air have to accelerate. Despite you being in a transonic airspeed regime or Mach number regime, the air with this extra acceleration can become supersonic. And once it becomes supersonic, there is a significant amount of wave drag. And that is part of your drag coefficient. And as a result, that will increase your drag overall and make your flight at that Mach number significantly more inefficient compared to slightly slower or a supersonic flight. The Mach number where your airflow above the wing becomes supersonic is called the critical Mach number. And theoretically, if your wing is infinitely thin, it can be exactly Mach 1, but of course all wings have a thickness, so for many older aircrafts, it's maybe Mach 0.9, or around that area. A thinner wing would have usually higher critical Mach number simply because it's thinner, so the air have to accelerate less in order to make room for the wing. That is why in aircrafts, especially fighter aircraft such as the F-16 and the F-104 Starfighter, the wings are significantly thinner than most aircrafts, and that is to reduce the drag and by increasing your critical Mach number. So here's how the supercritical airfoil work. For airliners, it is very difficult to actually have your wings significantly thin, out of 2 reasons. One, most airlines store the fuel in the wings, so if you make it thin, there's not going to be enough room for the fuel. Secondly, the structural loading for the wing will be significantly higher, and that will require you to either use more stronger materials or compromise some of the safety of the aircraft. So supercritical airfoil is like a compromise. It does still form the wave drag, it still have wave drag, but it does so in a way that is more controlled. It's all about delaying the formation of the shockwaves caused by supersonic airflow. And it does this in two ways. Firstly, the leading edge of the airfoil is thicker. It has a larger radius. The reason behind this is to provide a more gradual gradient of pressure. This can prevent the air from rapidly accelerating the moment it touches the airfoil, the wing. And that is this rapid acceleration is one of the contributors to why there is supersonic airflow at such an early state when the airflow passes the wing. The second way for the supercritical airfoil to delay and reduce the magnitude of shockwave is by having a flat upper surface. This can reduce the pressure gradient, the difference in pressure, and can reduce the amount of acceleration of the air. And the third characteristic of supercritical airfoil is the cambered trailing edge. That is there to compensate for the loss of lift, the reduced lift by the flat upper surface. So it's not necessarily a feature, it's more of a characteristic that's there in order to compensate for one of the features. So as a result, the supercritical airfoil can produce a weaker shockwave in a later stage. This can essentially reduce your wave drag, even though you are above the critical Mach number. You're being supercritical. There are a lot of applications of this type of technology, especially in newer aircraft. The first commercial aircraft that used this technology, supercritical airfoil, is the Vickers VC-10. All newer aircraft, including 787, A350, 777X, pretty much all the re-winged Boeing aircraft, all the modern Airbus aircraft, they all use this type of technology because it reduces wave drag and it reduces the seat coefficient of drag, and that will reduce the net drag of the aircraft. Another market within aviation that uses this technology extensively is business aviation, because business jets are focused on speed. One of the advantage over commercial aviation is its speed. It can travel to long distances in a shorter time, especially new aircraft such as the Citation X. The Citation X use both high sweep angle and also the supercritical airfoil in order to reduce drag, which can increase the top speed and also improve the fuel economy.